Hello everyone, Dr. Chen here. So we're going to discuss about capacitor in this video. The definition of capacitor is simple. So if you have two conductors, then they are separated by an insulator. It can be a vacuum. Vacuum is insulator, right? And those two conductors separated by insulator form a capacitor. So if you can apply a potential to these two conductors and they will carry equal amount and opposite sign charges. And the capacitance is defined as if you apply potential V to the capacitor, how much charge it can hold. So this is why we have capacitance means you apply V, how many charge you have. So it's charge over V give you capacitance. So if you hold 1 coulomb of charge when applying 1 volt, we call it 1 with capacitance is 1 coulomb per volt, and we also give coulomb per volt a special name called 1 farad. So let's study parallel plate capacitor. So you have two metal which are just parallel plates. Each plate has area A and they are separated by distance D. What would be the capacitance of this parallel plate capacitor? So we know from Gauss' law that if you have a plate, it carries charge density sigma. The electric field in between those two plates is going to be sigma divided by epsilon 0. And the sigma, of course, is charge density, so it's total charge over area charge density. So you replace sigma q of A, you find the electric field is q over A epsilon 0. Now we just learned potential difference for uniform field is E times T, and I know my E is Q A epsilon 0 times T. So this is my potential difference. We want to calculate what is C. C is by definition Q over potential difference between those two plates. So I keep Q here and I replace my delta V by this expression, and I cancel Q on numerator and the denominator. I got my capacitance for parallel plate is epsilon 0A over D. Now let me emphasize this equation. C equals Q over V is true for any capacitor. This equation, capacitance equal epsilon 0A over D, only applies parallel plate capacitor. So if we look a little bit more on this expression for parallel plate capacitor, you will find that if you can increase the area of the plate, you can increase C, and if you decrease the distance between these two plates, actually you can also increase C. So let's do a simple calculation for us to understand. So we have two plates, each with area 2 meters square in area, and they're separated by 5 millimeter. Then you apply a 10,000 volt potential on those two plates. And then we want to find out first what's the capacitance. So, and this is a parallel plate capacitor, right? So we can use epsilon 0 A over D to calculate what's the capacitance, put in all the numbers. Area 2 meter, separation 5 millimeter, which is 5 10 to the negative 3 meter. Faraday, so it's 3.6 10 to the negative 9 Faraday. This is the capacitance of this parallel plate capacitor. B, charge on each plate. You have V, you have C. So I have Q should be C times V. Now that's because C equals Q over V. So apparently Q equals C times V. I just found out my C. My V. So the charge is 3.6 10 to the negative 5 coulomb. And then I want to find out the magnitude of the electric field between the plates. So I have theta V equals E D for uniform field, so E is theta V over D. And I know my theta V is 10,000 volt. D is 5 10 to the negative 3 meter Newton coulomb. And this is the electric field between those two plates. This is for one single capacitor. Now, what's going to happen if you have more than one capacitor put in network? So first, let's study what's going to happen if you put two capacitors in parallel. So basically, you connect one end to A, another end to B. What is the capacitance of the capacitors inside this circle? So you can treat it as A and C equivalent B. So basically we want to find this one. So how many charge are carried by capacitor 1 would be C1 times V, and charge carried by capacitor 2, C2 times V. Because the potential difference over C1, V1, and the potential difference over V2, because it connected in parallel, so those two are equal potential. Those two are equal potential too, so V1 equal V2 and also equal to VAB, which is V. And also, the total charge carried on this side is Q1 plus Q2. Total charge carried by this side is Q1 plus Q2. So you can think of, you have Q1 plus Q2 here, Q1 plus Q2 here. So that's why I have Q equals Q1 plus Q2. So I have C equivalent equals Q over V, and my Q is Q1 plus Q2 over V. My Q1 is C1 times V, my Q2 is C2 times V over V equals C1 plus C2. So if you put two capacitors in parallel, the equivalent capacitance is just the sum of these two. If you have more than two in parallel, you just need to add the additional capacitance. Okay, now let's study what's going to happen if you put capacitors in series. So you have potential A, potential B, you have potential difference for C1, which is V1, potential difference for C2, which is V2, and you have potential difference, this is V1, right? And this is V2. We can visualize you have V1 plus V2 should give us V. And then, what's interesting, let's draw a box like this, only has the inner, these two surfaces. So this is C1, this is C2. Let's look at here. So those two plates, sides of the capacitor, are actually separated from everything else. So this is isolated system. So for isolated system, we have charge conservation. So if you start your C1 and C2 without any charge, you're not going to have any charge here. If you start your C1 and C2 charge neutral, right? And then you charge C1 and C2. But this H-shaped structure is a closed system or isolated system. You start with charge neutral. By charge conservation, the total charge in this structure is always 0. So even after you charge it, you're going to have equal amount of negative Q and positive Q. They have to add up to 0. So this is why Q1 has to equal Q2. And if you look at them as equivalent capacitance and say your capacitor has charge Q, so Q1 equals Q2, and it has also to equal to Q. So now we know C1 and C2 carry same amount of charge. Let's call it a Q. And we also know V equals V1 plus V2. And my V is going to be V, by definition, right, is Q over C equivalent. So this is V, C equivalent, and it carries charge Q. So charge Q divided by C equivalent give me V. V1 is Q1 divided by C1. But Q1 equals Q, Q1, C1. Q2, C2 give me V2. But Q1 equals Q2 equals Q, so which gives us 1 over C equivalent equal 1 over C1 plus 1 over C2. So this is how we calculate the equivalent capacitance for parallel plates. And when you only have two capacitors put in series, so you can rewrite this equation as C equivalent C1, C2, C1 plus C2. So this is a more general equation if you have more than one capacitor in series. How do you calculate the equivalent capacitance? So let's do one example. So we have C1, 6 microfarad, C2, 3 microfarad. What's the equivalent capacitance? Now is C1, C2, C1 plus C2, right? So of course it's coming from, say, 1 over C equivalent equals 1 over C1, 1 over C2. Putting all the numbers, we find it is 2 microfarad with equivalent capacitance. And then we apply a charge 18 on A and B. What's the charge carried by the equivalent capacitance? Q equals C total times VAB. Putting all the number 36 microfarad. And then we want to find out what is V1, what is V2. We already found the Q is 36 microfarad equals Q1 equals Q2 for parallel plate, for capacitors in series, and we already argued why Q1 has to equal Q2 equals the total charge carried by equivalent capacitor Q. So now I have Q1 and I know C1, so I can calculate what is V1. Q1 divided by C1. 36 over 6 volt, 6 volt. Similarly for V2 is Q2, which is 36.2 divided by C2. And then we can verify equals VAB. Okay, now this is two capacitors in connection. What's going to happen if we have more than two? So let's look at this example. A equivalent capacitance between B and C. So I have a non-PF capacitor, I have 11 PF capacitor. And how they are connected, right? Of course they are connected in parallel. So C equivalent in this case should be by adding them up. So let me do something. Let me call this one C1, this one C2, this one C3. So C, the equivalent capacitance between BC, let's call it C2, 3 in parallel, should be C2 plus C3, and is 20. It's 9 plus 11, so it's 20. Now I want to find the equivalent capacitance between A and C. So basically it's this capacitor and this capacitor in series. You have two capacitors in series. But so you have C1 and C2, 3 in series. So C1, 2, 3, which is the equivalent capacitance between A and C, is C1 times C2, 3 over C1 plus C2, 3. Plug in all the numbers. Find it's 8.6 pixel-farad. Okay, one more example. So I have C1, C2, C3 in connection as shown. I know what is C1. I know what is C2 and C3. Now I apply a potential VAB, but I don't know what is VAB, it seems. But I do know Q2. I know what is Q2. Then we want to find out what are the charge on C1 and C3. Okay, so first I know what is C2 and I know what is Q2. So from the fundamental equation, C equals Q over V, so which means I also know V2 is Q2 over C2. Q2 is 30 microcoulomb, C2 is 3 microfarad, so V2 is 10 volts. Okay, how is C1 and C2 connected? C1 and C2 in parallel. So V1 equals V2 equals 10 volts. Now I find out what is V1 and I know C1. I wanted to find out the Q. Q equals CV. So Q1 equals C1 V1. And the C1 is 6 microfarad. V1 is 10 volt. So Q1 is 60 microcoulomb. Q1 is 60 microcoulomb. Q2 is 30 microcoulomb. And C1 and C2 connecting in parallel. So you have 60 microcoulomb here, 30 microcoulomb here. And we say C12, which is the equivalent capacitance of C1, C2 in parallel, is in series with C3. So Q3 equals Q12. Now Q12, because C1, C2 connecting in parallel, Q12 is Q1 plus Q2, so it's 90 microcoulomb. So I found out it's Q3. And I found out V2 is 10, V1 is 10. I want to find out what is VAB. VAB equals V2 plus V3. So why I don't have V1 in this equation? This is because actually you have this C12 in parallel and C3. Those two are in series. You only need to add the potential for equivalent capacitor C12, and the V12 equals V1 equals V2. This is because C1, C2 is in parallel connection. The potential across C1 equals potential across C2, and the O equals to 10. So this is why I only put 110 here. You cannot put 210. So right now I need to find out what is V3. Good news is I already found out what is Q3. So V3 equals Q3 over C3, which is 5 microfarad. So C3 is 5 microfarad. So V3 is 90 over 5, 18 volt. So potential between A and B is 10 volt plus 18 volt. 28 volt. Okay, so that's all for capacitor.